Okay, hello, ninth and 10th grade World History and Cultures students. Today we're going to be working on chapter 16. We're going to get a good start on it anyway in World History and Cultures. We're going to start with our natural philosophers. We're talking about science. At the very beginning of the modern age, scientists were known as natural philosophers. The idea of natural meaning nature, philosopher coming from the Greek word meaning lover of truth, philo means love. And the idea that these philosophers were the lovers of truth concerning nature. They wanted to seek out the truths of nature. They loved the ideas behind nature. They wanted to seek out the secrets of nature. The term scientist was not coined until 1840. Before that, it was all about seeking out and loving the natural world. Okay, so the picture underneath this is a brain. You can see it is a mass of mostly fat and electrical impulses and pathways that allow us to think, breathe, imagine, and for our entire bodies to function. It is a miraculous organ, and very, very thankful for the brain that God has given us. Okay, we're going to talk about Nicholas Copernicus, who is a Polish astronomer. He proposed a new way of understanding the universe in his book, Revolutions of the Celestial Spheres. He is going to be moving diametrically away from the teachings that he grew up with. By the time we are into the Middle Ages, we are talking about an educational system that employed Thomism. Thomism was created by Thomas Aquinas, who created this idea that we needed to combine Romanism, Catholicism, and Greek paganism together, kind of mash that together, and then whatever came out of that was considered correct. Because during the time of the Renaissance, people had great respect for the ancient Greek philosophers. They had a lot of good things to say, but according to Thomism, it really wasn't appropriate to question the Greek philosophers. What they said was correct, without question. And so people who embraced Thomism, and specifically the Catholic Church, embraced this and encouraged the scholastics to teach using Thomism. They neglected to allow for questions to be asked, serious questions, not just questions for information, but to question whether or not the pattern of Thomism was correct, whether or not the philosophies were correct. Questioning Aristotle to the Catholic Church was the same as questioning the Pope and questioning God's word. That is not the way science is supposed to be set up. Science is designed specifically for people to question and to learn through questioning. So even today, we really encourage our students to use a scientific method to ask questions about something and to find the answers for those questions. So Nicholas Copernicus is going to promote the idea of the heliocentric or sun-centered theory. His idea was that the planets, including the Earth, revolve around the sun, and that the Earth is not a motionless body about which everything else in the universe moves. This is the exact opposite of what was being taught in the scholastic schools. This idea that the sun was the center of our system of planets was very new and very shocking to people during his day, because everyone was so involved with the geocentric or earth-centered theory. This was a concept that was originally devised by the ancient Greek philosopher Aristotle. He taught that the earth was the center of not just our solar system, but of the universe, and that everything revolved around our earth. That was not correct. And it was going to take a long time for people to actually become brave enough to question his theory. Johann Kepler was a German Lutheran astronomer. He dedicated his life to finding the mathematical harmonies in the mind of the Creator. He believed that God created the universe. He was a Christian. He did believe in the Bible. And his whole goal was to find the mathematical language that explained the universe as it was created by God himself. We need to remember that mathematics is the language of science. So if you want to be a great scientist, you have to become a great mathematician as well. So I strongly encourage you, if you are interested in the sciences at all, to really take every math class you possibly can. Learn it up, down, backwards, forwards, and sideways. Learn the mathematical theory that is available to you, and learn the mathematical train of thought that is available to you. It is a very different way of thinking about things. Mathematicians think of things very logically and very specifically. I'm a literature teacher and a history teacher. I think very differently than my son, Mr. S, the younger, who is a mathematical mind. And yet we find common ground quite often, because both subjects of history and literature versus mathematics and science, they all have a good foundation on reason. Okay, the 3 laws of planetary motion as discovered by Kepler, and he gave God the glory for all of these discoveries. He came up with 3 laws of motion. These are mathematical descriptions. First, he said that the planets orbit the sun on oval-shaped paths that are called ellipses. Ellipses would mean that they are on a long, narrow track rather than a circular track. If you go to a gym that has an elliptical machine, you know exactly what we're talking about here. It doesn't work like a bike where you sit down and you cycle in a circle. Your legs move in a circle. On an elliptical machine, your leg is moving on a long, narrow orbit that is oval shaped. Okay. The 3 laws of planetary motion also explains why the planets move faster when closer to the sun, because the sun has more mass. It's going to require things to move quicker next to it. And it explains the relationship between time it takes the planet to orbit the sun and its distance from the sun. And God got the glory from Kepler for all of his discoveries. Kepler did not look at this and say, I've learned this on my own. He gave God the glory for that. He was a Christian. Galileo Galilei was an Italian philosopher and scientist. He listened to what others were saying about the teachings of outer space, specifically Kepler and hang on, I forgot his name that fast. Copernicus. And he wanted to see if they were right. Oh, it's right there on the note. That's great. He wanted to see if they were right. He started to do experiments on his own. He used a telescope to do some of his own experimentation, and he used reason to deduce that the teachings of Aristotle had been wrong and Copernicus and Kepler were right. And he published a paper stating those very facts. And when the Catholic Church discovered that he was teaching and that he believed that Aristotle was wrong and Copernicus and Kepler were right, he was arrested and held until he confessed. It wasn't a real confession, but he confessed that he was wrong and that Copernicus and Kepler were wrong, that Aristotle was right all along, and that he was a big idiot for thinking that the Catholic Church could be wrong in the first place. So, of course, he made his statement. He said what he needed to say to get out of jail, and then went on and said, yeah, I really did mean it. I really do believe that they were right and Aristotle was wrong. Galileo also discovered the law of uniform acceleration, which states that the speed of a body falling in a vacuum, that means there's no air, no interference, it accelerates uniformly with time. If you dropped a penny off the Empire State Building, it's a really good example of this. The closer it gets to the ground, the faster the penny will move, because it's being pulled towards the Earth's center, that massive center. Okay, Galileo also calculated the laws of the pendulum. I can understand him here. He was in Mass almost every day. He would be looking around. There's beautiful paintings in Catholic churches, great sculptures architecture is fantastic, and you're listening to the same mass over and over again in Latin. And he got bored and was looking at one of the pendulum lights. This is a pendant light that you see here. Some of you may have a pendant light in your house, so you know exactly what we're talking about here. Any kind of shift in the Earth's surface, any kind of earthquake or movement at all, and the pendulum will move. And he was looking at this in a church one day, and he came up with this idea of studying the movement and the motions of the pendulum. So he created he calculated the laws of the pendulum that explained the relationship between the time it takes a freely swinging mass to travel in his arc and the distance between the mass and its connecting point. So the connecting point would be the ceiling, and the mass would be the end of the pendulum and how it swings in that arc. Back when we were a much, much smaller school, I had a classroom that was right off of the playground that was located in the fellowship hall. And whenever I taught this section of history, going through the different forms of scientific breakthroughs in history, I would wait till the playground was empty, and I would take all of my students out to the playground to find the pendulums on the playground. There are pendulums on our playground even today, and I'm sure you can figure out which they are, right? Swings are pendulums. And we would go have the students sit on the swings, and we would talk about the change of how quickly you swing based on how long the chains are on the swing set. So if you are on a swing that has a very, very long chain going all the way up from its apex, and you swing back and forth on that, you're making a very wide arc, but you are not going very fast. If you shorten the swing, shorten the chains on the swing, and you get in it, you start moving very, very, very quickly, but you aren't making a very large arc. You're making a very short arc. So that was a really interesting way to think about the laws of the pendulum. So if you have a swing set in your backyard, go outside and swing on it, and think about the laws of the pendulum, and just that it took somebody the time to figure out how long the chain must be for it to move in a longer arc. Isaac Newton, English philosopher who contributed more to the scientific progress of mankind than any other individual before or since. He had a brilliant mind for understanding God's most basic laws of the physical universe. And even though these were laws that people had known instinctively, he was the one who wrote them down and did repeated experiments based on what his observations. This is where the scientists really are important to us. We live our lives very instinctively. We know that if we drop something, it's going to fall on the ground. That's instinct. When you knock something off a table, you don't reach up to grab it, you reach down to grab it, right? Okay, if I'm going to drop a pencil, there it is, pencil, when I let go of it, you know it's not going to go up, it's going to go down. Well, people have known this for thousands of years, but it took somebody like Isaac Newton to say, why is that? Why is it that when we trip, we don't fall up? And so he was able to take something very, very basic and create a series of laws that helped us understand better the basic universe that we are in. So mathematical principles of natural philosophy, also called Principia, announced Newton's discovery of the universal law of gravitation. Now, today, people are trying to rewrite this part of history and saying that, well, you know that the law of gravitation isn't actually a law. It is just a theory. They're saying that because people are noticing that the laws of evolution aren't actually laws. They cannot be repeatedly experimented upon. It is really science by consensus. And to make it sound like, well, there is no way to prove something is a law, they have gone after this law, the law of gravitation, and said, well, you know it's not really a law. But when we look at how he presented the universal laws of gravitation. He follows everything that's in the scientific method. The evolution practice cannot do that because there was nobody there for the Big Bang. There is no way to recreate the Big Bang and do experiments, do controlled experiments, and to see if everything is exactly the same over and over again. So it can't be done in that area, but it can be done with universal law of gravitation. According to the universal law of gravitation, every particle of matter in the universe attracts every other particle of matter with a force directly proportional to the quantity of matter, decreasing as the distance increases. I'm a history teacher. I'm a literature teacher. Law of gravitation doesn't mean much more to me than go Newton. I'm glad you understand this, and I'm glad you had a passion for it. This is not my jam, but I can get behind you, and I can be your cheerleader. So learn the universal law of gravitation. And strangely enough, if you want to hear this sung as a pop song or as part of a pop song, you can look up Weird Al Yankovic's My Pancreas. He sings a whole song about how much he loves his pancreas, and about halfway through the song in the bridge, he sings about his pancreas being attracted to every other particle of matter in the universe. He quotes the universal law of gravitation in the middle of My Pancreas. You can say what you want about Weird Al, he's a genius. I refuse to disagree with that. Okay. Also with Mr. Newton, we have the 3 laws of motion, and these are a little easier for me to understand as a non-scientist. Inertia is the resistance to change in motion. I fight inertia every night. At the end of a long day, you just want to sit on the couch and watch TV with your feet up and just be all snuggly and tired and just sit there. It is really hard sometimes to get up off the couch to go to bed. Now, as nice as bed sounds, there is that resistance to change. I don't necessarily want to get up. I am inert. Okay, so I resist that change in motion. Now, I'm using a very simple example, but inertia is all around us. Everything is inert. It's resistance to change. It requires force for things to change. Then there's acceleration's relationship to physical force and action and reaction to force. And action and reaction is really easy to explain. You just think of a balloon. When you blow up a balloon, the action is the air rushes down if you don't tie a knot in the balloon. And the balloon goes up and makes a rude noise as it flies around the room. That is the reaction to the air rushing down. Do that experiment a couple times in a day and wait until somebody loses their mind. Actually, I really love doing this balloon experiment in class. It's so much fun, but we can't do that right now, so do it on your own. For his many achievements, Newton is known as the father of modern science. You've seen this picture many times on the Fine Arts slideshow in between classes. This is done by William Blake, who was a big fan of science. However, he was not a Christian. He started his own religion that included some elements of Christianity, some of paganism, and some of alien life forms coming to Earth and dictating man's life. But he was a big fan of Newton and created this painting of Newton almost as a god. Newton wouldn't have seen himself as a god, but this is the way William Blake presented him. He is holding in his hand a compass where he is actually calculating the circumference of the earth here, or something close to that, on a scroll that is also partly a tunic. And then he's got this elongated back with a couple of extra vertebrae. And then he is sitting very concretely on this piece of rock that is carved out specifically for his body type. But this is how Blake saw the new scientists or the natural philosophers of his day as gods. Optics was Newton's book about the nature of light. It was published in 1704, and we still talk about optics today, and specifically when we talk about the rainbow, how all white light actually contains every color of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv, the 7 colors that we see. So if you have yourself a a prism. You can do a little experimentation with that, and on colors. Andreas Vesalius, he is our next scientist we're going to talk about. He was a Flemish scientist known as the father of anatomy. This picture is a little bit on the side. These early scientists, and even earlier on, when we talk about Leonardo da Vinci, they had to fight really hard to understand the anatomy of the human body. And sometimes that required them to do some things that other people found really distasteful, like grave robbing. Grave robbing was a big thing among the early scientists, unfortunately. Usually the peoples whose graves they robbed were people who were criminals who were executed. Sometimes the executed body would disappear right off the scaffold before the executioner could even, dismiss the body to go be buried, but that was pretty rare. Usually what ended up happening is the body was executed and then taken to the cemetery, buried, and the people who buried the bodies were often hired by medical students to go back that night and dig the body back up, deliver the body to medical students, and then rebury the empty casket. So that was how a lot of the early scientists and medical personnel learned about the anatomy of the human body, was through grave robbing and using those donors. Today, you can donate your body to science. That's what my father did when he passed away. His body was donated to a university, and this is how doctors are trained and how to do surgery. They learn about the physical body by actually touching a physical body. And because the body is dead, they don't have to worry about pain. They can look at the same body repeatedly. They can figure out exactly whatever they need to locate on the body. It's a whole lot easier than using a computer program to figure out where certain organs and things are located. So that's a really important thing that people can do today. They can donate their entire bodies to science, specifically for the training of doctors. That's absolutely a necessary thing. So Andreas Vesalius, he published the first complete description of the human body in the 1540s, and this is part of it. This picture here, even though it may seem a little on the gory side, it shows really the beauty of the muscle underneath the skin and some of the nerves, and the way he has dissected really the arm to show off the beauty underneath the skin structure. In 1600, William Gilbert published De Magneta, the first great English science book. I know that's one of your homework questions, so double check your homework, make sure that you got that one right. De Magneta was the first great English science book. Okay, between 1614 and 1617, a Scottish mathematician and Bible scholar invented logarithms, nerds, and decimal notation, which I can actually get behind. The decimal notation is absolutely necessary for money. In order to make change, we have to know how much change is actually involved with that as well. For my son, Mr. S, the younger, I'm sure he can tell you all the benefits of logarithms, but this is the man who invented them. In 1620, Francis Bacon, an English philosopher, formulated the modern scientific method. That means he took and wrote it all out. This is what you have to do to prove something scientifically. So this is the scientific method. First of all, you have to establish that there is a problem. You identify the problem. That's a question. You collect information. You form a hypothesis. Usually it's a cause and effect kind of issue. Well, because this has happened, I'm assuming it's because of this problem. Then there is the procedure. You test your hypothesis to see if your hypothesis was correct. You designed experiments, and you have to design multiple experiments, and you have to perform those multiple experiments multiple times to make sure you always get the correct result or the same result. Next, you make observations about the experiments that you've performed, and you assemble tables and graphs, and then you take those observations and the tables and the graphs, and you write down whether or not your hypothesis was correct. You support it or reject it based on the data that you've collected, and you report and publish your results. When you report your results, you are showing it to other scientists, and they have a chance to redo the experiments as well. When we have regular school, we have a science fair every year, and for a lot of years we did experiments that had been done before by many students, but it's okay to repeat the experiment because that's a really important part of that. It's to learn, does this happen even though it's been done 50 times before? Is it still going to happen? And the answer is usually yes. There was a student, I can't remember who it was, who was very frustrated because the people who were judging the science fair marked her off because her data did not support her hypothesis. And she's like, but wait a minute. My data doesn't have to support my hypothesis. My data may say your hypothesis was wrong. And she was exactly right. If her data said that her hypothesis was wrong, that is still good experimentation. She's learned something. You don't have to go in. If everybody proved their hypothesis correct, no matter what the experimentation, then that would just be everybody living in this kind of dream world. We need to be able to prove whether or not our hypothesis or our educated guesses are correct. So she was absolutely right. She should have gotten a much higher grade, and I believe her teacher went back and took care of that for her. In 1628, an English physician named William Harvey discovered the circulation of blood in the human body. Everybody knew that if you stuck a sword in somebody, blood would come out. That was not a shocker. But he was the first to fully describe the circulatory system, including valves, veins, and the role of the heart. And in order to do that, he would have had to have a dead body to work on. He was also a personal physician to King James I, which was probably not the most fun job to have. James I was notoriously a problem to work with. But he was also a pioneer of modern embryology, which means he understood how babies formed. And he said, the examination of bodies of animals has always been my delight. I find that a little weird. I have thought that we might thence not only obtain an insight into the lighter mysteries of nature, but there perceive a kind of image or reflex of the omnipotent creator himself. So it wasn't like he was taking apart bodies for, fun. He was looking at the beauty of the structure. And then one of the reasons he wanted to discover more about the blood was because of scripture, and he's going to refer to Leviticus 17, 11, and 14, which says that the life of the flesh is in the blood. This is when God told the people of Israel that they should not eat blood at all. They should cook their meat thoroughly and not drink or eat blood because the life of flesh is in the blood. And William Harvey was quoted as saying, life therefore resides in the blood, as we are informed in our sacred writings, talking about the Bible. Okay, in 1631, French mathematician Pierre Vernier invented an accurate scale for measuring lines and angles. So we have a Vernier scale there for accuracy. I'm sure Mr. S. the Younger would be much more informative on exactly how this would work and how it would be used. So you can ask him. And then in 1637, Frenchman René Descartes, also known as the father of modern philosophy, developed analytical geometry and worked in several other scientific fields. He came up with what is known as the Cartesian form of geometry, Cartesian from Descartes. And he got that idea, according to one of my math teachers in college, from being sick in bed and looking up and watching a spider weaving a web in the corner of his room and coming up with the idea of Cartesian geometry. In 1641, a French mathematician and philosopher, Blaise Pascal, invented a calculating device that was a predecessor to modern calculators. He also perfected the barometer, which lets you know about air pressure and weather, and he helped to develop the science of hydrostatics. I am going to flip the slide a little faster than I would in the classroom, but you can always go back and rewind and get the slides, the notes here. In 1662, Robert Boyle, English scientist and Christian, formulated his laws of gases, earning him the title Father of Modern Chemistry. Before this time, chemistry was really not considered a scientific pursuit. It was considered more of a magical pursuit. It was the study of alchemy, which was the idea that you could take a base metal and make it into a more precious metal, like from lead to gold. So alchemy was the forerunner of chemistry, but Robert Boyle is the one who actually made it a scientific pursuit. In 1665, Robert Hooke, an English astronomer, mathematician, and experimental philosopher, became the first to observe microscopic cells, and he's the one who actually coined that term to describe these small particles that make up everything, cells. Cell was used before this, but it didn't describe the individual pieces that make up everything. It was used to describe small rooms in which prisoners were kept or in which monks or nuns lived. They lived in these very self-contained cells. That was their rooms. And then we have one more. In 1675, a Dutch naturalist named Anton van Leeuwenhoek, he was known as the father of microbiology. That's the minuscule or microscopic biology, living things. He designed and built simple microscopes and observed protozoa, that's protozoa right there, and anatomical functions. I'm not even sure how to address that. But he is the first to actually look through and see these microscopic critters. They're still alive. Okay, that is where I'm going to leave you today. I've got 2 more slides that actually show microscopic protozoa and like viruses and disease. I really don't even know what they are. I think one is a virus and one is a bacteria. They're really pretty. That's why I put them on the slideshow. But while you're looking at those and I'm just kind of talking over it, I just want to remind you, do your homework a little bit at a time so you're not overwhelmed. Remember that you do have literature to take care of. I won't be addressing you again until Monday. Obviously, take your weekend off. And I'm hoping that you guys will join the school on Friday at noon. There's going to be a Good Friday service. And then on Sunday, if you don't have a church that you are live streaming, please feel free to live stream Mountain Avenue Baptist Church. And I will talk to you again on Monday. Have a really great weekend and happy Easter. Bye.